We have talked about thermodynamics for electrochemical system, and for fuel cell, the open circuit voltage is a very important thermodynamic parameter that relates to thermodynamics or basic electrochemistry. So first, let's look at the fuel cells that operate at, for example, 25 degrees C. Here we list two types of fuel cell. One, it operates on proton. The other one operate with hydroxy group. One could be alkaline fuel cell operating on hydroxy group. The other one could be the just the PEM fuel cell. Okay, the anode half cell reaction. The anode half cell reaction, which is the oxidation half cell reaction, we write it in reduction format, would be if the conducting ionic species is proton, that would be proton plus electron to form hydrogen. Actually, for anode reaction, it should go the other way, going from hydrogen to proton, but I just write it as a cathodic reaction or reduction half cell reaction. And then, not surprisingly, at 25 degrees C, the standard electrode potential for this redox pair, for proton-hydrogen pair, would be 0 volt versus SHE, a standard hydrogen electrode. Then, for proton, for cathode half cell, for reduction half cell reaction would be for oxygen gas molecule to combine with proton and combine with electron cathode, meaning reduction. Oxygen molecule got reduced to form water molecule. Okay, so we have 4 hydrogen on the left, 4 hydrogen on the right, 2 oxygen on the left, 2 oxygen on the right, 0 charge on the left, 0 charge on the right. So this is cathodic half cell reaction. And then based on the standard electrode potential theory for this oxygen O2 water redox pair, the standard electrode potential, again this knot or circle represent the standard electrode potential for this redox pair is 1.229 volt versus SHE, standard hydrogen electrode. Okay, and then for the full cell or for the overall reaction, again would be combine the anode and the cathode half cells, or combine the reduction and oxidation half cell with the goal to eliminate electron. Then we would have 2 hydrogen molecule combined with 1 oxygen molecule to form 2 water molecule. Okay, and the standard cell potential would be the standard electrode potential for the cathodic or for the more positive one minus the standard electrode potential for the anodic or the more negative one. So it would be 1.229 volt minus 0 would be 1.229 volt. That gives us the full cell and associated standard cell potential. Okay. On the other hand, let's say if we have an alkaline fuel cell, if the ion species that conducts through the electrolyte is hydroxy group OH minus, then for the anode, for the oxidation half cell, it would be still hydrogen combined with 2 hydroxy group to form 2 water molecule and release 2 electron. Okay, you see 4 hydrogen on the left, 2 plus 2, 4 hydrogen on the right, 2 oxygen on the left, 2 oxygen on the right, 2 negative charge on the left, 2 negative charge on the right. And if you check the standard electrode potential theories, the water hydrogen pair, previously it was proton hydrogen pair, but in this case would be water hydrogen pair. The standard electrode potential versus SHE would be minus 0.828 volt, minus 0.828 volt, which means the hydrogen can be easily oxidized into water. Okay, On the cathode, on the reduction half cell, it will be oxygen combined with electron and 2 water to form 4 hydroxy group. Okay, so you see 2 plus 2, 4 oxygen on the left, 4 oxygen on the right. 2 times 2, 4 hydrogen on the left, 4 hydrogen on the right. 4 negative charge on the left, 4 negative charge on the right. Okay, so this would be our cathode or reduction half cell. And the standard electrode potential for this oxygen O2 OH minus pair would be 0.401 volt versus SHE, more positive than SHE. Okay, which means it's difficult, it's easier for oxygen to get electron and difficult for OH group to release electron. Okay, and then the overall of full cell reaction would be to combine these two half cell reactions with the goal to eliminate again electron. Eliminate electron. Okay, and then if you combine it, we would have the same full cell reaction: 2 hydrogen molecule combined with 1 oxygen molecule to form 2 water molecule. And the standard cell potential would be the standard electrode potential for the more positive cathodic minus the more negative or anodic, which is 0.401 volt minus 0.828 volt, and it turned out to be 1.229 volt. So whether we have having proton or we have hydroxy group as the ionic species, as long as the full cell or the overall reaction is the same, we would have the same standard cell potential, which is expected because fundamentally we're just reacting the same species, hydrogen and oxygen, to form water. Of course, we should have the same standard cell potential, no matter whether the electrolyte conducts proton or conducts hydroxy group. Okay, this is a very important point. You may have different types of fuel cell. If the temperature is the same, the overall reaction is the same, you should have the same standard cell potential. Okay, and then note these two above reactions. When we refer to water, we always refer to liquid water. The ionic species are aqueous solution. And sometimes if you want to know what would happen to the standard cell potential if the water exists in, if the water generated, at least some of it is in vapor, then we need to consider the actual step between water, liquid water, and water vapor or gas phase of water. Okay, and there will be an additional free energy change between for liquid water to go to water vapor. And if you check the database, such as Janef table, we would have the delta G 0 from liquid to gas, from liquid water to water vapor, the free energy change. G for gives free energy, delta means change. This naught or 0 means standard state. Gives free energy change would be the formation energy for the gas phase minus formation energy for the liquid phase, and then we would end up with a number of 8.559 kilojoule per mole. That will be the free energy change from liquid to gas on the standard state for liquid water under 1 atmosphere into 1 atmosphere of water vapor. Okay, and then if we consider the fuel cell, the cell standard potential, if we consider water vapor, it would be, remember what we said, the cell potential would be free energy change over minus NF, and free energy change would be the fuel cell free energy change when we consider liquid water plus this additional step, the free energy change from liquid to gas. Okay, and then the first term, the liquid water over minus NF, that will be just that will give us the standard cell potential for liquid water, and then this delta G from the free energy change from liquid to gas, that gives us one additional or correction term if we want to deal with water vapor, okay, as a product. So this term for liquid water, the fuel cell standard cell potential for when the product liquid water would be 1.229 volt minus delta G0 would be 8.559 kilojoule per mole divided by NF. N would be 2, F is 96,485 coulomb per mole. And if you work out the mass, it would turn out to be slightly lower, 1.185 volt. The standard cell potential would be 1.185 volt if the product in the above reaction is not liquid but water vapor. Okay? Apart from fuel cells that operate at low temperature, even at ambient temperature, 25 degrees C, there are, as we said, solid oxide fuel cells or molten carbonate fuel cells that operate at high temperature. But fundamentally, for these high temperature fuel cells, if we use hydrogen as the fuel, the overall reaction is still hydrogen gas combined with oxygen gas to form water. It's still the same fundamental reaction. Then from electrochemical engineering point of view, the equilibrium cell potential would be the standard cell potential minus RT over NF ln of reaction quotient. That's what we learned before. And then if we want to expand a little bit, the standard cell potential would be the Gibbs free energy change. Standard Gibbs free energy change, delta G0, G for Gibbs free energy, delta for change, 0 or not for standard state over minus NF. Okay, that this term corresponds to the standard cell potential. And the minus, and then we have RT over NF ln reaction quotient. Reaction quotient is product activity raised to the power of the stoichiometry coefficient. So water activity raised to the power of 2 over reactant activity, hydrogen activity raised to the power of 2 and times oxygen activity. Okay. So this gives us, in principle, the way to calculate equilibrium cell potential. And then let's say if we can, how do we find free energy change? Delta G0 standard free energy change. Remember, free energy change would be the formation, Gibbs formation energy. F for formation, Gibbs formation energy, not for standard state formation energy for product minus reactant. And the reactant, you don't forget that's the stoichiometry coefficient. We have 2 water, so we need 2 here. We have 2 hydrogen, so we need 2 here. And it's reactant, so we need minus product minus reactant. And then, of course, oxygen. And then the formation energy for pure substance under its standard state, like hydrogen gas or oxygen gas, would be 0. So then the reaction Gibbs free energy change on the standard state would just be 2 times the Gibbs standard formation energy for water. Okay? And so we can further rewrite the above equation. The cell potential, equilibrium cell potential, would be delta G0, which is 2 times delta GF0H2O. The water Gibbs formation energy under standard state over N for this reaction, for totally 2 hydrogen molecules, so totally 4 electrons got transferred. So 4, N would be 4 times F minus RT4F ln this reaction quotient. Okay? And if we check, let's hypothetically high temperature fuel cell, let's hypothetically say at 1000 Kelvin, 1000 Kelvin, 727 degrees C. From the thermochemical data, such as the Janef table, you can check the standard Gibbs formation energy for water in the vapor state, in the gas state, would be minus 192.59 kilojoule per mole. Okay, this number you get it from Janef table for the reaction Gibbs free energy change. And then if we know our fuel mixture, quite often the fuel would be hydrogen water mixture, 97 of hydrogen, 3% of water at 1 atmosphere. The oxidant would be air, which means activity for oxygen would be just the partial pressure of oxygen divided by the standard pressure would just be around 0.2921. Okay, with this information we can calculate the equilibrium cell potential. Minus we keep 2, we keep the Gibbs formation energy for water, we put that number minus 192.59 kilojoule per mole here. For F, 4 times 96,485, okay, minus RT, R 8.314 joule per mole Kelvin, T 1000 Kelvin over 4F, 4 times 96,485 coulomb per mole times natural log of the reaction quotient, and the water activity is 3%. So it would just be 0.03 raised to the power of 2. The hydrogen is close to 1, but not exactly 1, 0.97 raised to the power of 2 times activity of oxygen, which is 0.21. And then if we plug the number, we would get the first term minus be positive, 0.998 volt. The second term is minus, but then the natural log of a number smaller than 1 would be another negative, so it would turn out to be positive 0.1185 volt. So then you add up, overall the equilibrium cell potential would be 1.12 volt, which is close to the number that we got for low temperature fuel cell. But this is an actual fuel, not the it's not the standard cell potential, but the cell potential for this practical fuel and practical oxidant. Note that oxygen is the activity is not 1 but 0.21 because we are using air, and the hydrogen and the water, we mix them together. Water is a product, hydrogen is reactant, and they have certain concentration, so it give us a voltage that is not somewhat different from the standard cell potential, which is 0.998 volt. This term would be the standard cell potential, and that's a correction term to correct for the activity. Okay.